Hello everyone, once again welcome in my this video of the one-way design slab. Okay, and this is part 2. In this part 2 I am going to teach you the rest of the load value, calculation of the factored load, calculation for a depth, check for a depth bending moment criteria, design of the main steel, okay, and design of the distribution steel. Up to this I am going to teach you in this video, so keep watching and keep learning. Okay, so in part 2 I am going to take some this basic value for you guys. Okay, so what is the main thing is that up to this is our step number. Next step I call is the 4 number step. Okay, and I take the different color, okay, for you all. So now if I'm going to this is my step number, next step. So here we are going to what calculation for factored load. Okay, the calculation of the factored load, which is nothing but called a W, but it is U. Okay, so it is defined as a factored load. So how this term is get solved? First one is get self weight of slab. Okay, self weight of slab, which is nothing but BD gamma, B multiplied by D multiplied by gamma, right? So B is nothing but what we have. B is 1, depth we know is 0.13, we calculated, and gamma for a concrete reinforced steel is 25. If it is only concrete, so we take as a 25, so we get the value is as a 3.25 kilonewton per meter. Okay, so this is value we got. Now the next step is that second one is that the finished load. So what exactly the finished load is? Finished load is floor finish, which is given to you, okay, which is given to you in a numerical. Okay, it is 0.5. okay, and in for part number 1 I already listed all this value. 0.5 equals to what exactly? 0.5, okay, kilonewton per meter. Okay, now third one is that the live load. Okay, live load is nothing but what exactly? 2.5 multiplied by 1 is equals to it is 2.5, okay, kilonewton per meter. Okay, so now all this value what I got 3.25, 0.5 and 2.5. So when I get add this all the value, that means 3.25 plus 0.5 plus 2.5. okay, so what we get exactly, the value we get is 6.25 kilonewton per meter. Okay, so what the value we got, if we multiply 6.25 multiply by 1.5, so we get the total value is as the 9.38. why I use 1.5 over here? Because if you wanted to make any load the factored load, okay, if you wanted to make any load factor, so we have to multiply by 1.5. it is given in IS code, okay, 456. it is page IS 456. according to IS 456 we make it for IS factored load. Okay, so we get the 9.38 kilonewton per meter. So according to this, with respect to this value 9.38 value, okay, we have to solve the numerical. Okay, we have to solve our total design of calculation numerical. Okay, so now we got this 9.38 as what our WU. Okay, this is what we got W. Now the step number 5 I take the different color to you guys do not make any sort of the changes. So 5, in this 5 we are going to calculate the calculation for the factored bending moment. Calculation for factored bending moment. Okay, so this value we are going to take. Okay, so calculation of the factored bending moment is nothing. What factored bending moment is defined by M, but the factor is made by MU. You can see over here that also U is assigned as a factored load. Okay, so U is, if U is attached to that particular symbol, so or particular the representative value, okay, so it is termed as to be factored. So now the MU, the formula, now you know that why I am going to wait a minute. So now MU, okay, we know that our slab is simply supported slab. Okay, in first video I already told you, okay, it is simply supported slab. So formula for a simply supported slab is really very simple. Okay, it is by W L square by what much? 8. Now we have the WU and LE effective length, right? effective length I calculate in the first part. Okay, so WU is nothing but what we have the WU, we calculate your 9.38. So 9.38 multiplied by what is the effective length is 3.111, okay, at the last of the part 1 divided by 8. So what we got, the answer is we got as a 11 point, okay, 11.35. Okay, first we got in a kilonewton into meter. If I convert it in a newton per mm, newton into mm, okay, so it is 11.35 into 10 raised to power 6 newton into mm. Okay, so this value I got right now. Okay, so 11.35 into 10 raised to power 6 newton into mm, the value I got right now. Okay, now after that I go for my next next calculation, which is nothing but step number what? Step number 6. In step number 6 I am going to solve the check for depth from bending moment criteria. Okay, check for depth from bending moment bending moment criteria. Okay, so according to bending moment criteria we are going to check the depth. So how we can check? So it is really very simple. What is your bending factor bending moment? We are going to compare it with mu limiting moment. Okay, so we are going to use M20 and Fe415 steel. Okay, so which is a torch steel. So mu what we got as a 11.35 into 10 raised to power 6 newton per mm square. That's for this reason only I convert it to kilonewton to newton into mm square. After that I going to change, I use for Fe415 the mu limit is given as 0.138 FCK BD square. Okay, so FCK BD square. So from this we are going to calculate the depth. What we have to check? We have to check the depth. Okay, I already having the depth 111. Okay, so now we have to check depth. What is the required depth? Okay, what is the required depth for our the design purpose, and what we take? Okay, we take some depth. Okay, 3.111 what you have seen over there. Okay, so we are taking some depth. This is not a depth, this is what effective length. Okay, so we take some depth which is a 111 mm, okay, which is effective length. So we wanted to compare, and from this we are going to define this effective length also. When we get the effective length, we compare this depth, this coming depth of the calculation, and then and only then we can assign that this depth what is coming over there, it is the required depth. Okay, and what we take is a 111, it's our design depth. Okay, that for that 111 we are going to design, but requirement is different. Okay, so we can put all the value 11.35 multiplied by 10 raised to power 6 in multiply by 0.138. What is the FCK we have is a 20 multiply by what is the B is 1000. Okay, multiply by D we have to calculate. Why I take the B is 1000? I take as B as 1000. Okay, so just calculate. If I calculate this D, I got the value is 64.13 mm, and what I already calculate the D from the in first part as a depth is a 111. I'll show you, okay, how that 111 come. Okay, wait a minute. It is over here. This is one. Okay, so the effective depth, okay, which is 111, and what we got right now for what we are going to check. Okay, here we are going to check the value, and according to changing the value we got D as a 64. So it is less, no? So we are required this design for the design parameter, and we have this value. So that means our design, what is our depth is safe. Okay, so depth is now safe for us. Now we are going for the different calculation, like the calculation for the steel also. Okay, so our step number 5, in step number 5 I take a new color. Okay, so in our step number 5 I going to tell you what is the design of main steel. These all the 4 steps are really very important. Okay, if you find out it helpful, please like my video and please subscribe my channel. Okay, guys, please subscribe my channel, because I'll get motivated and you will get more the videos from me. So please try to understand, and please subscribe my channel always. Okay, so guys, you all know what is the formula for the formula what we have for the AST. For this numerical of the one-way slab is a determination of the design of the main steel. Okay, so next step I taken as a design of main steel. Okay, so design of main steel is really very important. Okay, in the any sort of the numerical, the main steel and distribution steel is really very important parameter which concern. Okay, so in this part 2 topic, I covered the factored load calculation and main steel and distribution steel. Okay, so main thing is that if you not subscribe my channel, so please subscribe. Okay, and let's start to the calculation. So now main calculation is like that. The AST what you have right now, the formula for the AST is very simple: 0.5 FCK upon Fy. Okay, in bracket 1 minus under root of 1 minus, okay, 4.6 mu upon FCK BD square. Okay, FCK BD square multiply by B into D. Okay, so this is what exactly formula for the AST. Okay, with respect to this formula, what we have to do, we have to put our all the value, and as we can put our all the value, then we have to add our the we can get our the AST main designs main steel. The design main steel is what is the main value, main steel area. This is the area of steel we get. Okay, as the area of steel we get, okay, then we can simply determine the with respect to that area, we can simply assign that is AST equals to n multiply by pi by 4 multiply by diameter square. With respect to that, if you put a particular diameter, or instead AST, you can know number of bar you wanted to provide. Okay, pi by 4, there is nothing is you have to change over there. You can get the diameter value. If you, instead of if you put the diameter value, you get number. Okay, instead of in both this or this number or diameter, between two you have to just make you have to make sure that you have to put only one value, then you get another value. Okay, so first of all you have to return AST. Remember, this formula is really very important. Okay, in your all calculation of the steel and sorry, in RCC. Okay, so now I'm going to put all the value 0.5. okay, FCK is we know all is for 20, it is for concrete, and 4 and 5, that means F5 for steel. Okay, 1 minus under root, what is 1 minus 4.6 mu. We already calculated the bending moment, factored bending moment 11.35 into 10 raised to power 6. Okay, divided by FCK we know is 20 multiply by B we taken as 1000. Okay, and D we calculate, but it is 63 point something, but we take as a what we get in the part number 1 is 111. Okay, for which we are going to design, multiply by simply 1000 multiply by 111. Okay, so the AST we got, the value is already calculate all the value. Okay, so no need to get a calculation over there. It's 300.2 mm square. Okay, so this is what the area of steel we got, AST we got right now. Okay, we in mm square. So this is what the main AST we required, but we have to know, we have to check what is a minimum AST, minimum amount of AST required. Okay, what is the minimum amount of AST required? For that, the IS code take at IS 456. Okay, I'll just give you some pages of the IS 456 page number. From that you can simply find out this all the value, all the formulas also. Okay, so it is a for the minimum of the steel. Okay, the formula is assigned by the IS 456.12% of the B into D, where D is not a smaller one, it is not a effect to D, it is a capital D we have to take. Okay, so it is a capital D. Okay, so the value is 12 percentage. What is the B we have right now? Okay, and the D we already take is at 130. Okay, so when we calculate, when we solve this value, so we get 156 mm square. So guys, for our the minimum, this slab, our 156 square AST only required. Okay, but we have how much? 300.2 square AST. So comparing with this two, it's almost double of the given AST right now. Okay, so our AST is what set. Okay, now we are safe in a depth and we are safe in a AST also. Now we further going for our next calculation of the depth. Okay, so what we are going to provide, we are going to provide the 300 mm, 300.2 mm square, 0.2 mm square AST. Okay, in our slab, right, which is a one-way slab. Now the next thing is that we have to provide the spacing. What is exactly spacing? Spacing is nothing but, if consider this is our slab. Okay, in slab the the steel is placed, that is the main steel is placed in such a manner. Okay, assume that. Okay, I am not going to tell the exact AST. I'll tell you the exact AST in the next part. Okay, the spacing is nothing but the distance between this 1, 2, 3, 4. That means what is the spacing between the bar. Okay, that spacing we have to calculate. Okay, so this spacing is really very important and we can calculate in this following manner. So it is calculated like that. For IS, in IS code 456, the formula is given to you all. Okay, so main formula is pi d phi square, that is diameter square, multiply by 1000 upon what? 4 into AST. Okay, so the formula in simple manner is pi by 4. Okay, into, that is different for, okay, same formula I write in a different manner. Okay, to understand you, pi by 4 into diameter square. Okay, divided by AST. Okay, multiply by 1000. Okay, if you wanted to that means remember this formula, the main formula is this. Okay, you have to just follow this formula. Okay, I'll highlight this formula. Okay, this formula we have to use, spacing equals to. Okay, so now after getting this formula, we are going to solve another one, the second one. That means with this formula we have to calculate one value. Okay, we calculate over here. Next formula is the spacing is also given as a 3 into effective depth. Okay, and third, add the spacing is taken as a 300 mm. Okay, we have to take the minimum of this. Okay, the minimum value of this, sorry for a sound, minimum value from both 3. Okay, so both of 3 we have to take minimum value. So it is, I'm going to put all the values. So pi by 4 diameter square, what the diameter I'm going to use, I already assume in part number 1 8 mm square. So 8 multiply by 1000 divided what AST I have 300.2. Okay, sorry guys for background, so it's really very noisy. Wait a minute. It's really very noisy. I'm really very sorry for that. Okay, so now so after putting all the value, I got one value is 167.64. Okay, I can say that it is a 160. Okay, or 170 mm. Okay, now or I take 160, whatever you want to take. Okay, 3 into D depth I have write 111. Okay, right, so it is a 333 mm, right, and this T, so minimum of this what 170, so I take this value. Okay, so I am providing spacing equals to 170 mm spacing I am going to provide. Okay, and I am going to provide 8 mm square diameter bar. Okay, at the rate of 170 mm center to center distance. So these were the sentences we can make with respect to this spacing. Okay, now you get that how the sentences come, that we are going to use 8 mm diameter bar with the spacing of 170 mm center to center. right? Or you can take at a 160 also. Spacing is not the bigger, spacing is maybe its maximum is 300, okay, but along with your the reinforcement what your steel you are going to provide, with respect to that you have to take all the value properly. Now after this is what main steel. Now after getting, I wanted to provide the distribution steel also. Okay, so design of the distribution steel over the next part. Okay, I'll take a different color for that. Okay, so design of distribution steel in one way slab. Okay, so how we can do this? It is really very simple. Now what we have to go, I wanted to provide 6 mm, I wanted to provide 6 mm dia, okay, dia which is Fe 250, okay, grade of steel. Okay, remember these things. Okay, what we have to going to do, design of distribution steel in one way slab. I wanted to provide 6 mm diameter of Fe 250 steel. Okay, so now first of all we have to determine the AST, but what distribution. Okay, so how we can determine this? It's really very simple. For distribution steel, we have to take 0.50% of B into D. Okay, this is formula coming from what? IS 456. Okay, this is your Indian IS code actually, guys. For if you are ASTM American Society, then you can use your IS code, but the process is same. Okay, so 0.15, that means is 0.50 multiplied by what is B we have is 1000, and total depth is what we have is 130. Okay, so I get the value for a distribution steel is 195, okay, m square. So with respect to that, okay, I'm using I determine the spacing. So spacing formula is not going to change, formula is same. First spacing SV equals to, or spacing equals to pi phi square into what 1000 divided by what 4 into AST. Okay, just put all the value, that is pi by 4 into what is diameter square is over there, I mean 6 mm square, 6 square multiplied by 1000 divided by AST over 195. Okay, so we get the value as 41145 mm. Okay, 145 mm, this is value we are going to use. Now second one is what? Spacing equals to is what? 3 into D. Okay, so now what is 3 multi sorry, what is not 3, sorry, it is, we have to take another 5D. I'm really sorry, I made some mistakes also always. So it is as a 5D. Okay, so 5 multiply, what is the D we have? 111, right? So we get as a 555D. Okay, so no need about to take the third one is as a S equals to 450 mm. So we have to take minimum, so obviously we have to take 145. Okay, so now the spacing we have to assign as a 145 mm for a distribution steel. Okay, so our sentence in this manner is in such a manner that I just changed somewhat. Okay, we provide what we are going to provide. We are providing 6 mm square dia bar, okay, at the rate of 145 mm center to center distance, right? So this is what we are going to provide. Okay, so this is exactly we are want for a distribution steels. For now we got the steel for a main reinforcement, and we got the distribution steel also. Okay, now with respect to that, in our next, this is our part 2 end over here. Okay, in our next part I am going to discuss with you the check for shear, then check for deflection, okay, check for development lane, and in last video I'll explain you what is the reinforcement diagram for the this numerical. Okay, so keep watching, keep learning, and please subscribe my channel, and have a nice day, and bye bye.